Okay, so here's what we were talking about last time, surfaces in R3, and we made this observation about how to write them, which is convenient. And then this example about cross sections. So you can take horizontal cross sections simply by throwing in an additional equation, that equation being the equation of the plane taking the horizontal cross section, right? So there's an algebraic process that corresponds to this geometric process of looking at the cross section. Okay. All right. And if you know enough cross sections, like here we have the horizontal cross sections. We have a bunch of vertical cross sections. You could do vertical cross sections the other way, setting x equal to constants. Right? Taking cross sections like that. Write down the algebra, draw the little parabolic cross sections, and you piece it all together, right, and get a reasonably good idea of what the surface looks like. Now, let me show you a different method. I think this is really, really nice. The book underemphasizes this, in my opinion. It's a special case. Does not always work. Not all equations have the required condition, but if it does, this is awesome, right? So here's how it works. If your equation involves x's and y's only in these forms, and I claim that that surface is rotationally symmetric around the z-axis, which is a huge amount of information to know, and I'll show you an example of how useful that is in a minute. But first, let's try to see why this is true. Let's consider this point right here, and then let's consider what happens if I take that point and I'm going to say rotate it around the z-axis, by which I mean, draw a little radius arm there, perpendicular to the z-axis, right, and then rotate that little radius arm around to get you to this point. Let's talk about this green point and this blue point. They have different x coordinates, granted, right? They have different y coordinates, sure. But x and y, keep in mind, don't really ever appear by themselves. X and y only appear as part of these forms, right? So the x's and y's at these 2 points might be different, but the square root of x squared plus y squared is the same for both of these points, because square root of x squared plus y squared is that distance. And all we did was rotate that little radius arm around the z-axis. So as far as the x's and y's that appear in this equation are concerned, these 2 points plug in the same way, right? Also, notice that these 2 points have the same color choices, the same z-coordinate. Because when you rotate around the z-axis, you don't change the z-coordinate. So different points, different coordinates, but as far as this equation is concerned, they plug in exactly the same. So if one of them is on the surface, then so is the other one. And if one of them is not on the surface, then neither is the other one. And that means it's rotationally symmetric. Everybody on board? See how that works? This is a really neat observation. Now let me show you how you put that to good use. Let's consider this equation again. Now, we drew a bunch of pictures on the previous page of cross sections, and let's remind ourselves, this is artistically challenging to draw that picture, right? And it took me a while to draw. That's one of the nice things about this projector solution, right, for teaching, is that I don't have to draw this picture live in class, and it would take me a minute or two to make a decent, it's non-trivial effort. It's not my first time doing this, right? So that's hard, but the argument here is easy. I observe, by the way, look how x and y appear in this equation. They appear only in this special form, and therefore, this thing's rotationally symmetric around the z-axis. I therefore only have to look at one cross-section. I'm going to look in the cross-section where x is equal to 0. That's that plane. If x is equal to 0, that term just goes away. And all I'm left with is z equals y squared, which is a parabola in that plane. I know it's rotationally symmetric, and I know one of the cross sections, so just rotate that cross section around the z-axis and bowl. Done. Right? Everybody happy with that? This is much more convenient than this game here. Okay, so now again, the condition, this doesn't always happen, right? But you do have to have, it's not just that you need these forms to appear. It's that you need x and y to appear only in that form. If there's any stray x's or an e to the y or a cosine cubed of x, something like that, forget about it, right? This argument doesn't work. It's not rotationally symmetric, and you just have to, sadly, you got to play these games. Right? But anyway, keep an eye out for when stuff like this might happen. So here's a couple of examples where we just did this one. Here's a variation. Let's look at that guy there. Now, x and y don't appear in the desired form, but I think you guys can think through for yourselves an analogous argument here. Y and z appear only in this special form. Square root of y squared plus z squared. That's distance from the x-axis. By the way, draw yourself a little picture. Persuade yourself that that's the case. Square root of y squared plus z squared is distance to the x-axis. Analogous arguments. This surface is rotationally symmetric around the x-axis. Right now, okay, that alone doesn't resolve the problem, but it does mean all I have to do is look at any one cross-section. I'm going to look at this cross-section here where z is equal to 0. If z is equal to 0, plug that into there. This term goes away. I have x equals y squared. That's an easy, what am I doing? That's an easy parabola. X equals y squared. Sitting inside of this plane, that is. Looks like that. Rotationally symmetric around the x-axis, and we get that picture. Everybody happy? Okay. All right, very handy. So some games for y'all to sort of play through for yourselves. What does that look like? What does that look like? Right, it's analogous arguments. Devil's in the details. Think through the details, right? By the way, let me observe. Let's go back to this example here. Why did I pick this plane, z equals 0? Why didn't I pick, that plane where y is equal to 0? No reason. Whatever. Suit yourself. It doesn't make that much difference. If you do it in this plane here where y is equal to 0, let's see what we get. Here we have y equals 0. That means that that goes away, and I get this x equals z squared, which is that parabola. Rotational symmetry argument, I get the exact same surface. Right? So take your pick. Pick any plane that you want. Now, obviously, in order for this argument to work, we need to pick a plane that includes the axis of symmetry. Right? So don't pick that plane up there. It doesn't make any sense. Right? So you have to pick a plane that actually includes that axis. In fact, if you want, you could even pick a half plane. That's really technically all you need is just enough so that when you rotate it around, you get the whole thing. But pick any one you want. Okay, hyperboloid. Now I'm going to work this example out for reasons that I'll explain in just a moment. But you can see right away this is going to be susceptible to the same kind of an argument. Right? Look what we have here. X and Y appear only in the special form. So we know that this is rotationally symmetric around the z-axis. So I arbitrarily pick a plane. See, I guess I'll pick that plane there. Let's think through what that plane is. That is where y is equal to 0. If y is equal to 0, then this term goes away. We have then remaining x squared minus z squared equals 1. And here's why I'm doing this example. You got to make sure you remember all that business about hyperbolas from Algebra 2 class in high school, right? So you're likely to be a little rusty on that. I'm going to make sure to think it through and make sure you remember which way it goes. Right? My own personal cheat is to think about which of these two variables could conceivably be 0. Right? So let's ask the question here. Could x be 0? In this, looking at this equation here, would it be possible for x to be 0? Well, if x were 0, I would have a negative of a square being positive. And that doesn't make any sense, right? So that's not possible. So it is not possible for x to be 0. That means that the hyperbola in question cannot intersect that red line right there. And that means that it can't be that hyperbola, right? That's not possible because that goes through that red line. That has points where x is 0, and that's garbage. Yeah? Okay. All right. So that means it has to go the other way, and thus it's like this. And so then, of course, you got to think through, all right, well, what happens when I take this hyperbola and draw it, rotate it around the z-axis, and well, you get this, I don't even know what to call this thing, but let's see here. Let me pick a color. You get this, whatever that is. So anyway, it's called a hyperboloid. But in terms of what does that look like? It doesn't look like a bowl, or I don't know what common everyday item to name that as. Yes?
So that's like rotationally symmetric, even though it's not exactly in the form that we just talked about.
Oh, but it is in the form. Yeah, no, it absolutely is, right? Let me look at the equation here. X and Y appear only in the given form. Yeah.
So the z squared doesn't really matter.
For making an argument about rotational symmetry around the z-axis, the only requirement is that x and y appear only in this special form. Yeah. So, yeah, sure, z's are going to appear in whatever way, but that doesn't affect this argument here. Right? What that does affect is kind of what the resulting eventual shape looks like. Yeah. Yes?
Could you go over the reason for that one more time?
Why don't you rewind the tape and listen to it again? Okay, because we're behind schedule, and I'm trying to play catch up ball. But by the way, this is a great idea, and I want to encourage everybody to do this. If you don't quite catch something the first time, you just want to hear it over again, that's what the recording is for, right? So just make a note somewhere that I want to go back and check the tape, and you can totally just listen to it again. Yeah, absolutely. Okay. So this is another example. I'm going to be quick with this one. Now, this example here. It doesn't, look, x and y don't appear in the special form, and x and z don't appear in the special form. And you see these minus signs, and it's easy to kind of think, well, I need something squared plus something squared, and there's too many minuses. But notice that you can rewrite things as long as you're legal, right? You can rewrite as x squared minus y squared plus z squared equals 1. And so y squared plus z squared right there, right? So y and z appear only in the special form. And the fact that their sum is being multiplied by -1 afterwards is fine. Who cares? No problem. Right? So this is rotationally symmetric around the x-axis. Make the usual cross-section argument. Cross-section looks like this. Rotationally symmetric around that. Rotate it around, and this is also called a hyperboloid. This first one, this is called a hyperboloid of one sheet because there's only one connected component to it, and this two sheets is because there are two separate connected components. Right? There's kind of this bowl, turned sideways, and then there's this totally disconnected thing here. Okay, so thus two sheets. All right. I also like to think of this sometimes as, two eyeballs in a staring contest. That's a little creepy, but funny. Okay, here we go. Hyperbolic paraboloid. By the way, all these names are in the book, and you're supposed to know these names. You're supposed to know what is a hyperboloid, what is a hyperboloid of one sheet, hyperboloid of two sheets. Please don't just memorize, this equation means this thing. There's just too many different ways that the minus signs can be different. There's 8 different ways that you can put the minus signs. There's 8 different versions of this. And, of course, you can write them differently because you could take this 1 and move it over to the other side and have x squared plus y squared minus z squared minus 1 equals 0. So that looks different. So depending on how you choose to view this, there could be as many as 16 different variations of this. So if you just memorize your way out of this problem, that's not good. Plus, let me remind you, what we're looking for on exams is ideas, right? So if on an exam I were to ask you, this equation, draw a picture of the surface described by this equation and, argue how you got to your conclusion. If you just say, I got to this because I remember that this was in the book, right? You did this as an example in class, therefore, right? So that's not reasoning, right? So don't just memorize them. But anyway, when a hyperboloid, a rotation of a hyperbola, ends up with one sheet, that's called a hyperboloid of one sheet. Make sure to know these names. Oh, by the way, paraboloid, these are called paraboloids, rotations of parabolas. Okay. So this one's called a hyperbolic paraboloid. Scary sounding word for a Pringle, right? So how do you draw this? Well, let's see. What rotational symmetry can we take advantage of for looking at this equation? And sadly, none. Right? No matter how you rewrite this, you're not going to find a way to rewrite this where it's x squared plus y squared and combined with stuff involving only z. It's not what this is. So sadly, it's not rotationally symmetric. So don't make a rotational argument in this case, right? A crash and burn situation. So sadly, you have to make cross sections. So let's think about some cross sections here. Let's set x equal to various constants. When you set x equal to various constants, you're going to have cross section planes looking like this. Right? Setting that x equal to a constant, various different constants. What you see is we have the resulting equation gives you upward pointing parabolas, but they're upward pointing parabolas which, as c increases, are shifted down, right? You see that minus sign right there. They're shifted down by different amounts. Let's see, let me draw some more of these parabolas. They're shifted down as indicated by that minus c squared. Everybody on board? So, you got to think through. This is one of these hard artistic challenges of how do you draw these cross sections, and then how do you, in your mind, kind of see it all coming together as a surface. So, practice your drawing. Drawing is important in this kind of business. Practice thinking three-dimensionally. Buy a can of Pringles. Right? And just try to persuade yourself that, that you can take these kinds of algebraic situations and combine them in this way and get these sort of conclusions. Yeah.
On the exam, will we be expected to draw?
Certainly on the homework. On an exam, I'm not going to say that I won't ask such a question, but I will say that, in the interest of self-preservation, I don't want to. It's really hard to grade art, in a math class. So, that said, you can look through my old exams and see some examples, but what I can do is say, give a geometric description of what does this surface look like, right? And then, technically you don't have to draw it, but if you can draw it, it sure helps, right? And you can instead, depending on how the question's worded, of course, you can say, well, this is, I'm no good at drawing this, but we have, here's what the cross sections look like, and it's kind of like a Pringle, right? In which case, cool, so this is all fair game. Yeah, definitely. By the way, to the question of drawing, if students come to me on a regular basis at times like this in Math 212 and say, okay, but I'm no good at drawing. What should I do? The answer is get good at drawing. Right? So there are things to know about how to draw three-dimensionally. I'd be happy to explain them to you. Come to my office hours. I'll give you my little standard 15-minute pitch on how to, 10 minutes, on how to do decent drawing of three-dimensional things. And not beautiful drawing necessarily, but functionally acceptable, decent, drawings. That kind of thing. By the way, for your curiosity, if you're looking and thinking to myself, oh my gosh, I never would, but that's an amazing Pringle and I would never be able to reproduce that. It took me a while to draw this. I went through a bunch of bad versions. I did not put this straight onto this page. I had practice pages, and once I got one that after erasing and fixing and messing with it, then I traced it onto this page. Right? So I cannot just freehand a Pringle like that. So it's hard to do. And so anyway, it's maybe worth practicing a little bit and realizing that sometimes artistic challenges are, in fact, quite hard. Okay. Yeah. So how do you know that this is a Pringle? Well, so we know that there's parabolas that are shifted down if you look at it in that direction. Or you can view it as if you take your cross sections this way, you're setting y equal to various constants. That means that you're going to clearly have upside down parabolas that are shifted up. Right, the up shifts you can see like that, and then the downward pointing parabola you can kind of see like that. Yeah? Everybody on board? Okay. All right. Last, you can also set z equal to a constant. That means you're taking a horizontal slice, and notice that you get a hyperbola, right? And horizontal hyperbolas. All of this is consistent with it looking like a the more common terminology for this is a saddle, because Pringles hadn't been invented back then. Anyway, so that you get this shape because it has these different kinds of cross sections, and thus the name hyperbolic paraboloid. Okay, all right. Okay, so what if you have this equation? All right, what do you do with that? Well, you could make a rotation argument, sure, but I want to take this in a different direction. Different way to approach it is to say, well, I don't know about this equation, but I do know about that equation. That equation says distance from the origin is 13. That's a sphere. I can draw spheres. Right? For example, this point, 3, 4, 12, satisfies that equation. Right, is everybody happy with my assertion that that's a sphere? Looking at the equation, distance to the origin is 13. Again, is what that says. Okay. All right. So, what do you do with this? Note the 2 right there. So this is a different equation. It's not the same equation, therefore it does not represent the same surface. But gosh, there's a lot of similarities there. Is there some way that we can use our understanding of the equation and surface on the left to help us understand this equation on the right? Wouldn't that be nice? It seems pretty plausible, in fact. So, in fact, if you take this point, this blue point right here, right, and you plug that in, well, it doesn't work anymore. No surprise. Of course, it's a different equation. But let's try to break down a little bit more specifically why it doesn't work. It doesn't work because this 3 that got squared, okay, well, that's still happening. This 4 that got squared, okay, well, that's still happening. But wait a minute. Now, this 12 that had been being squared, that 12 is not being squared anymore. It's being multiplied by 2 first and then squared. And so I'm looking in this arithmetic over here, I'm looking at the wrong numbers getting squared. And that's why the arithmetic doesn't work. Yeah? Okay. So the hack then is to say, how about I divide by 2 first, and then when I'm in the equation have to multiply by 2. Now I'm back to 12 being squared as it was over here, and now that point works. Yeah? Okay, so there's a nice punchline then. When you do this process, when you replace in the equation, when you replace z with 2z, it's like you're taking all the z coordinates and dividing them by 2. You have to divide the z coordinates by 2 so that, let me say, in preparation for having to unexpectedly multiply them by 2 later. Okay. Well, let me say it a little bit differently then as well. This algebraic process of replacing z with 2z squishes the surface, right, by a factor of 2. It's a magnification. It's the reverse of a magnet. It's a squish, right, by a factor of 2 in the x direction. So this is an example of kind of a general rule of, as you manipulate algebra, how do the equations get manipulated? And the general rule is whatever you do to the variables in the equation, what I'm going to call the opposite happens to the surface. Okay, so for example, we've already discussed that this is that guy, right? So, well, what does that mean that I can conclude about this? Now, well, what I've done here, I have replaced, in this equation, I have replaced z with minus z. Everything else in the equation has stayed the same, right? So because I'm putting a minus sign in front of the z in the equation, what's the opposite of multiplying by minus 1? Well, coincidentally, it's multiplying by minus 1, right? So that means that all the z coordinates get multiplied by minus 1, therefore we get a flipped parabola. Everybody happy with that? Okay. All right. Okay, so for example, let's look at this this surface here. Well, excuse me, this equation here. Golly, it's kind of vaguely reminiscent of the equation of a sphere, but there's several changes that have been happened, and I claim you've got to think it through for yourselves here. But what's happened here is what had been an x has been replaced with x over a, and what had been a y was replaced with y over b, and what had been a z was replaced by z over c. So it's like we started with x squared plus y squared plus z squared equals 1, which I know is a unit sphere. Right? But because of replacing x with x over a, here, in fact, let me do this. Replacing x with x over a, that stretches by a factor of a in the x direction. Right, and etc. Y gets replaced by y over b. That stretches it by a factor of b in the y direction, and etc. in the z direction. So now you got to think geometrically. What happens if you take a sphere and stretch it by certain factors in these different directions? And I hope y'all remember from Algebra 2 class that when you stretch a circle, you get an ellipse. Right, so what we get here is a stretched out version of a sphere, but stretched in such a way that all the cross sections are now ellipses instead of circles. So we call this an ellipsoid. In fact, do this. Ellipsoid. Yeah. Okay. All right. Analogous arguments for the rest of these. You start off with x squared plus y squared equals z. Oh, we know what that is. That's that paraboloid that we've already discussed. So this is that surface. And now, apparently, we're stretching by a factor of a in the x direction. We're stretching by a factor of b in the y direction. We're stretching by a factor of c in the z direction. And you stretch out that little purple paraboloid, stretch it out in the different directions like so, and you get another paraboloid, but this one with kind of elliptical cross sections, and so we call this an elliptical paraboloid. Yeah, pretty good. Questions? Yep.
Is that still rotationally symmetric around the z-axis?
I'm sorry?
Is that still rotationally symmetric around the z-axis?
No, sadly it's not. So now this was, right? But when you stretch it all out of shape, it's just not. It doesn't have that symmetry anymore, and you can see that by, algebraically play the game, try to figure out how you can rewrite this with the x and y appearing only in the special form, and you just can't do it unless a and b have the same absolute value. Yeah. Anybody else? Great question. Yeah. So there's a temptation to say, there's my x squared plus y squared, but that's not algebraically legal. Yeah. Okay. So this is called an elliptical cylinder. I'm going to let you guys think it through, but you can kind of see the algebra where this came from is clearly a cylinder, right? It says x squared plus y squared is 1, means distance from the y-axis is 1, so cylinder, right? Circular cylinder. And we're just going to stretch it in the x direction by a factor of a. We're going to stretch it in the z direction by a factor of c. And so we get cylinder shape, but with elliptical cross sections, and thus, again, the name. Everybody happy with that one? Okay, do be careful if there are multiple deformations happening. So let's look at this one here, and you look at the, what we've got here, and you can see, okay, well, look, we're taking x and we're subtracting 1 and then dividing by 3, and so there's a temptation to say, okay, well, then we, translate by 1 and then stretch by a factor of 3, and that's wrong. So the devil's in the details. Now I'm just going to show you the one example of this, and then I want y'all to henceforth be very much on your toes as you apply these. If there's more than one deformation happening, don't try to do it all in your head, right? Per the following example. Now I'm going to first do the stretch. So I replace x with x over 3 first. Now you're thinking, well, that's not the order of operations. Aren't you supposed to do that? In the algebra, it's x minus 1 over 3, right? So shouldn't I do the minus 1 first? Well, just keep in mind, in some sense, we're kind of undoing, right? We're making, we're changing inputs to undo changes that happened in the algebra. So we're kind of end up going backwards through the process. But anyway, more to the point, just see how this plays out. This stretches out by a factor of 3. Right? This original sphere gets stretched out by a factor of 3. Having done that, replacing x with x minus 1 shifts by 1 in the x direction. Now, a lot of students get uncomfortable at this point and say, "Well, but that's not really the x." And really, isn't that kind of really x? Sort of, because that's where it came from here, and it's just wrong. If you want to work from this algebra, then you have to work from that surface. And feel free, but we already took a step away from that. This is now what we're looking at, right? So completely forget about all this stuff that came above, right? Where we started, that's ancient history. We're done with that. That's x. That's the x that's relevant to this algebra, to this picture in this algebra. And so it's replacing x with x minus 1. Shifts by 1. Yeah? Everybody on board? So notice we went in seemingly sort of the wrong order. We did the division first before we did the subtraction, but it seemed to all kind of fall into place. And that's really the kind of the natural way to do this. Now, yeah, question.
Why can't you just think of it the other way?
Yeah, you can. Yeah, that was going to be my next observation. If you want to take this and rewrite it as that, you're totally fine, right? So you could, in this algebra here, let me zoom back in. You could take x and turn that first into x minus a third, right? So that's a translation. And then subsequently, you could replace, so let's see, so here this is the translation, right? And then you could subsequently replace x with x over 3. Like so, right? That's totally fine. It's just going to be a harder picture to draw because, for a combination of reasons. First of all, now we're dealing with fractions. That's weird, right? And second of all, if you one nice thing that happened in this argument here is notice that when we did the stretch, we were stretching coincidentally from the center of the thing that we're stretching. Right? It was a centered sphere, and we're stretching from the center of the sphere. In all cases, when you do a stretch, you're stretching away from, you're stretching along the axis, away from the origin, away from the plane, the coordinate plane. So in this case, we're stretching away from the ZY plane. If you have taken, if you have already done a translation, right, then you're going to have an off-center sphere that you're then stretching, but you're not stretching it away from its own center, you're stretching away from the origin. And so it's like you have this, asymmetric stretch, and it's just a lot harder to kind of see what's going on in that process. So I feel like this down here is the more unnatural and less convenient way to do it. It does work, it just doesn't work very well. Right? Does that answer your question? Mm-hmm. Cool. Anybody else? Okay. All right. Right. Okay. So let's move on. All right. So functions of several variables. So we're in chapter 13 now. Come to think of it, I guess we've been in chapter 13. No. Well, anyway. So we're in chapter 13 now. Let me tell you what a multivariable function is. You all know what a function is, right? They tell you this in middle school at some point, I think. But a function, something goes in, something comes out, right? And the way they very often phrase it is number goes in and number comes out. In general, a function does not have to take in a number and spit out just a number. A function can take in any. You could have a function where sets go in and colors come out. Or, here's a weird one, and this is a real mathematical thing. There are functions where the thing that goes in to your function as other functions go in, and then maybe numbers come out, or different functions come out. So a function's a very general term. Something goes in, something comes out. What these somethings are, hey, whatever. Right? It's pretty wide open. Right? So a multivariable function, something goes in, something comes out, sure. Okay, what goes in is a bunch of real numbers. Go in. And then what comes out is a bunch of real numbers. Thus the name multivariable function. Okay. All right. Now, here's a nice sort of shorthand for this. Recall, if you have a bunch of numbers in order, well, you could just call that a vector. That's what algebraically, this is how we represent vectors, is as a list of coordinates. Right? So these bunch of numbers going in, we can say that that's a vector that goes in. And these numbers that come out, we can say that that is a vector that comes out. So this is very convenient, if only for notation. This is very convenient. Common terminology, by the way, when you have a vector being the thing that comes out, a function like this is routinely referred to as a vector-valued function. You're going to hear me say that term all the time. Vector-valued function. Okay. A little bit of notation. When you have a situation like this, right? This notation is pretty common. So we've got this function f. What goes in is points in this set, right? X comes from the set Rn because there's n variables, right? And what comes out is in this set Rm because there are m outputs. So we'll say, just for notational convenience, we'll say this is a function from Rn to Rm. And it's just a way of saying what kinds of critters go in and what kinds of critters come out. Right? Okay. So here's another very common notation. The way you might think of this notation is I want to talk about this function f. So I'm going to tell you its name. This function's called f. Now let me tell you a little bit more. Here's what you need to know about f. It goes from Rn to Rm. Right? So this notation, very common. Hope you'll be ready for it. Oh, a little bit of terminology. The set that the inputs come from is called the domain, right? And the set that outputs have to go into is called the target. Little side note, some of y'all might have heard the term range. That term is problematic in ways that we'll talk about more in Math 216. The problem is I'm going to try to keep myself brief here, but the term range has been used to mean slightly different things. Sometimes the word range is used to mean target, but sometimes the word range is used to mean something importantly different from the target. Very similar looking, but importantly different. And so because that term is it's in effect ambiguous because it's used in different ways by different people. Well, then, okay, we need to be able to speak without confusion. We can't have a Tower of Babel situation here. So I and a lot of other people like to just use the word target, and there's no ambiguity about what target means. Okay, so here's an example of a vector-valued function, and very often we'll just write this. Now notice that what goes in here, the input to the function is not just one real number. The input to this function is 3 numbers, right? It's if you want to think of it this way, a vector in R3. Right? Notice that what comes out is not just a single real number. What comes out is an ordered pair of real numbers computed by formulas that are written down there. Right? So there's 2 separate formulas for these separate output values. So what comes out is a vector in R2. And just for naming convenience, we might give those output variables names. For example, here V1 and V2. Okay, and then again, vector notation, very convenient sometimes. Okay, so let's see some examples. This is an appropriate one. Right, so the weather function. This is going to be an interesting function in the next week here. Oh, yeah, question. Yeah.
When we go from R3 to R2, is it always one down, no matter what?
No. You can have functions from R2 to R7. You can have functions from R1 to R1. Whatever. No constraints there. Totally. Okay, so here's the weather function. What I'm calling here the weather function. If you give me a longitude, a latitude, and a time, right? Well, we can talk about what's the weather at that point on the surface of the Earth at that particular time. And there will be a certain temperature, certain barometric pressure, certain humidity. Right? So, inputs, outputs. It's a function. Right? So it's a common misunderstanding. Students look at multivariable functions and think, these are arbitrary. Mathematicians like to take nice, normal, reasonable things like real-valued functions and let's consider weird, irrelevant ivory tower abstractions based on those, and let's study those. And confession, yes, we do like to do that, but that's not what's happening here. Okay, these are really, really easily, naturally relatable things. Like so, a multivariable function here describing the weather. Nothing abstract about that. If you're in a business, well, gosh, you're interested in wanting to know how profit depends on some things, but you're also interested in risk. So I hear. I don't really know any economics, but those things depend on, well, they depend on how much capital do you have to invest and how many employees do you have hired and what are the interest rates, relevant kinds of interest rates for your situation. So these things that you want to understand are functions of these variables that cause them to do things. Right? So you are studying a multivariable function. And by the way, notice, why did I stop at just 3 variables here? Right? If I knew more economics, I could rattle off a few other inputs that affect risk and profit, and I don't know exactly what they are. Advertising, maybe. Something like that. Right? So the point is, you can have functions with more than 3 variables, right? And it's nothing spooky. There's nothing crazy about that. It's perfectly normal. We're just running a small business here. Okay, there's nothing abstract going on with this. Okay, so don't get creeped. Don't assume that all math happens in R3 or less, and anything above that is, just mathematicians being weirdos. No, the real world is highly multivariable in dramatic ways. Okay, so that being said, how do we draw pictures of multivariable functions? I only have a couple of minutes here, but I do want to talk about graphs. The first thing I'm going to say about graphs is that graphs are not the only pictures that we're going to use to draw multivariable functions. Now, let's flash back to single variable calculus. In Calc 1, pretty much every picture you draw is a graph. It's so ubiquitous in single variable calculus that I for a while along in there, I kind of didn't understand that a function and y equals that function weren't the same thing. I just kind of thought, well, that's what y is. Y is the function. What else are you going to do? It's just, I'd never done anything else with a function. Right? In my Calc 1 classes, this is always the picture you draw. So the first thing y'all are going to have to get accustomed to is that is absolutely not the case in multivariable calculus. We're going to draw different kinds of pictures. We're going to take a function and make a picture out of it in a completely different way that is absolutely not the same as setting the output values equal to y or some other variable, z or w or whatever, right? So there's going to be importantly, structurally different kinds of pictures that we're going to be thinking about. So when I talk here about what is a graph, don't conflate the word graph and picture. This is just one way of drawing a picture to help you understand a function. So anyway, that said, here's how that works. Whatever your function is, set its output value equal to some other variable y. Look for all points that satisfy. Now keep in mind in this equation, the inputs and the output all in the same point. Right? So a point on the graph is not a point in the domain. A point in the domain only has in coordinates. A point in the domain would be like this x1, x2, through xn. There's not a point in the domain. A point on the graph is this weird, arbitrary other construction. So, for example, if you have a function from R2 to R1, such as here, we can set the output values equal to this new variable called y. That gives us an equation involving 3 variables. An equation involving 3 variables gives us a surface. Right, so the graph is then that surface there. Something like that. And again, now very convenient, very useful. We're going to do a lot of things with graphs. I'm a fan. Just don't overbuy into this concept of graphs. This is just one of many different ways that we're going to draw pictures, and it's very important to understand the distinction, because when we start writing down calculus, the calculus of graphs, I'll call it, is very, very different from the calculus of these other kinds of constructions that we're going to talk about. So you've got to make a clear distinction in your mind of what kind of a picture am I looking at before you start thinking about how am I going to interpret the calculus in these different contexts. Okay, see y'all later.